Good evening, everybody. Well, this short video is in response to a flat earther named Mr. Gary WYBENGA or WYBENGA. Please forgive me for mispronouncing his name. However, let's just call him Gary. So Gary comments on my videos, which is fine. I have no problem doing that. The only issue I have is his occasional slip up when he uses ad hominem, which, as I've said before to other flat earthers, does nothing for you, for the person, for your victim. It only diminishes you. Okay, so it does nothing for your cause, but it certainly diminishes your standing. So don't do it. It's not. It has no value at all. It doesn't bother me in terms of making me feel bad. I just find it useless. Okay, so enough of that. So this particular video then is going to have a look at his assertion that that as things go away in the distance, you will be able to see the bottom of it go first, just as we do observe, and he thinks that that can happen on a flat earth. He goes through great pains to show us that that the higher up you go, the more you can see on a flat surface, and that's true. Yes, the higher up that you go, the more you can see. That's self-evident. If the earth was flat and you went up high enough, you'd be able to see the whole damn thing, wouldn't you? So it's obvious. But that's not what we observe in terms of what the objects on this surface looks like. So when we look at an object on a spherical surface, we notice that as it goes away into the distance, as it goes over the horizon, it disappears bottom first. In other words, you get to see less and less of it from the bottom, and until you can't see any more of it at all. And its angular size change is not that dramatic. Okay, so you can still see it quite well, even though some of it, or nearly all of it, has gone beyond the horizon. By the same token, when you're looking at an object on a flat surface, even though you can see beyond that object as you rise in elevation, in other words, you're seeing further and further into the distance, the object doesn't. You don't lose any of the object. You just simply see the object get smaller and smaller. So its angular size gets smaller and smaller, but none of the object gets lost to your vision. This just gets smaller and smaller until the point where you can't resolve it anymore. Okay, now that'll happen on a flat surface. Of course, on a spherical surface, I'm talking about using a lens, you can watch the object disappear, and it won't disappear because it's getting smaller and smaller so that you can't resolve it. That's not what the problem is. The problem is it's falling below the horizon. Whereas on a flat surface, the problem is it's getting smaller and smaller to the point where you can't resolve what it is. That's quite different things. So let's have a look at my board again. I've done this a few times, but here we go again, okay? Okay, I think you can see the whole board now, practically. Let's move it a bit further, right? Okay, I'm pretty sure that you can see the whole board. Okay, so what have we got here? Now, I'll try not to go too deeply into the mathematics because, you know, from flat earthers' point of view, that's probably not something that they'd be interested in anyway. but I'll just mention it very briefly for those other people who are interested in this. But have a look at this. So I'm depicting this object, and that's that can, this can over here. We'll talk about the can later, you'll actually see it. So this can here, this object, okay, is going over the horizon. And as you can see, the surface of it is not linear. So it's going over, and as it reaches the horizon, sitting on top of the horizon, falls below the horizon, and even further down, and then of course at this point over here you can't see it. But as you can see, this surface is actually a curved surface. So if you were to compress this, say in a camera, you would notice that it's a curved surface. A perfect example of this is the Lake Pontchartrain bridge. So if you have a look at that photo, you can see this effect taking place. You can actually see the curve over the water if you compress the film. So this is exactly what this is depicting over here. Okay, so you can see it's a curved surface. It's not linear. In fact, these lines, if you like, here representing the distances compared to distances in the horizontal direction compared to distances in the height, your elevation, okay, you will find that this over here is not a linear equation. And if you did plot that, and this is a circle, which it is, then on an XY graph, so Y meaning elevation, X meaning distance, then Y would be equal to the square root of X squared minus R squared, where R squared is the radius. Okay, and if you plotted that, if you did plot this, that means your elevation against the distance, you'd find that it in fact it turns out to be a circle. Okay, now let's have a look across here. Here we have the same thing where we've got this can again moving into the distance like this, and as you can see that regardless of how far you go, the can just gets smaller. It just gets smaller. So yes, as I said before, if you go up in height, you will see more of the distance ahead of the can. You'll see more of it if the higher up you go. So you'll get to see the can a bit further away. Now, but the difference here is that this here is linear. Okay, so this is a linear function over here. This is a circular function. This is a linear function. Okay, so as this goes smaller and smaller and smaller and smaller and smaller, the Rayleigh formula will actually give you the proper distances and measurement and angles for that, angular size for what that would be, and you can actually look that up. But it's a linear. It's in a linear function, a linear proportion. So linear meaning x and y. So for a given distance x, you have a given elevation. So, or for a given elevation, you will have a given distance, whatever that is. So this represents the gradient. Now a linear equation would be y equals mx, where m is the gradient. Okay, and then over here x represents the distance. Okay. All right, so if you don't understand the maths, don't worry about it. You should be able to have a look at this, and you can see that this will be this is the actual observation. This is real. This is real. This is what we actually observe. Things will go over the horizon and over the curve, and it's curved like this, whereas the fictitious flat Earth would actually this would just keep going. And by the way, I've got infinity up here because that's what would happen. This would just keep going on to infinity. And how far, what distance that would be, how thick that would be, if you like, would depend on your elevation. Okay. All right, so the higher up you go, the more of this from here to here that you'll see. Okay, you'll see more and more of this. They'll go more and more higher up like that. If you are higher up, as you get further down, this will squeeze down, so you'll see less and less of this. Okay, that's what happens on a flat earth, if this was a flat earth. But that's not what happens in reality. In reality, this is what happens. Okay, all right. Okay, so I think that pretty much covers it. So what I'm going to do now is I'm going to stop here and then let you have a look at the can that's on my bench, and that should tell you, that should give you a visual on how that works. It's pretty crude because I mean it's just sitting on a kitchen bench, but I think you'll probably get the idea. There's the pièce de résistance at the end of it. Look out for that, because I'm sure you're going to enjoy that. Okay? All right. Back in a sec. Okay, so here we are at my bench, and in front of me is a small can. And I'm at this point, I'm just about at the bench level, and as I go higher and higher, I can see a little bit further on the bench, and as you can see, I can actually see past that can, so I can see further and further. This is a flat surface as I get further up, which is expected. Now I'm going to move the can a bit further away and we'll have another look. Okay, so now you can still see the edge of the bench, and I'm going to raise the camera up, and as I raise the camera up, so in other words I'm going up in elevation, I can see that past the bench. Okay, here we are again. So now what I've done is I've moved the can a bit further along. As you can see, that's the edge of the bench, and as I move the camera up, I can see beyond the can. So as I go up, I can see further, and the other thing I can observe is I can see the top of the can, whereas if I go down lower in elevation, I can't see the top of the can now, the absolute top. Okay, so up we go again, and you can see beyond the can. This is a flat surface. We'll move it a bit further and check again. Okay, here we are again, and all I've done is move the can further along on the bench, and I'll get down a bit lower. Okay, you notice I can see the whole can. I move up, I still can see the whole can. There's none of it's missing. And I move higher and higher, and if I move right up there, I can actually see the bench top that's beyond the can. Okay, so there we go. Trying to hold this over my head. Okay, now here comes the pièce de résistance. Okay, here we go. Have a look at the can now. This will never, ever happen if the earth was flat. You notice the can is over the horizon. That's what it would look like if this was a curved surface. The can, we only get to see less than half of the can. The bottom has disappeared. As you can see from this demonstration I've just given you, that would never be possible on a flat surface. What you see in front of you there could only happen on a curved surface. Okay, so Mr. WYBENGA, this debunks your video once and for all. Okay, here we are back again. It should be pretty obvious to you now what the difference would be if the Earth was flat compared to the reality where the Earth is obviously spherical. So clearly the observations that you see, that you actually see, are based on a spherical Earth. The Earth is spherical. That is why you see what you do. Okay? If the Earth was flat, it would be completely different. Just have a look once more. As you can see, the reality is that the Earth is spherical, so here we have this going in a spherical way across the surface, getting smaller and smaller and smaller, but as it goes over the horizon. It's not a significant change in angular size, it just simply goes over the horizon and then disappears. This one over here only disappears, if you like, in the distance, because you can't resolve it anymore. So if you had a better and better lens, you would be able to keep seeing it. Over here, no matter how good your lens is, you will not see it. So over here you can use a telescope to see what this is over here. Over here, at this point here, where it's gone, you can use a telescope till you're blue in the face. You are never ever going to see that again. Over here, you use a telescope, you look at that one over there, that little one over there, you are still going to be able to see what it is. I think if you just use your common sense, that will become obvious to you. Shall I repeat it? If you use a telescope over here on your fictitious flat Earth, you will be able to look at that can again, right away in the distance, no matter how small it is. You won't be able to resolve that with your eye, but you will be able to look at it with a powerful enough lens, like a telescope. Over here, in the real situation, when that's gone over the curve, that will get smaller and smaller, eventually it'll go over the curve. You will not be able to see it with any kind of lens. There's been no telescope which will allow you to see this can again. I think that should be pretty obvious. Okay, thank you for watching the video to the end. If you have, and if you want to watch more videos, please hit the subscribe button and the like button. Don't forget to hit that one, or the dislike button if you in fact dislike it, and then I will do some more of these. Okay, thank you, see you next time.